In this lecture, we shall find the shear force and bending moment values for a simply supported beam with a triangular and symmetric uniformly varying load acting over the entire length. As usual, we will first draw the schematic diagram of the beam supported by a pinned support at the left end and a roller support at the right end. Let's label them as A and B respectively and mark the length as L meters. Let's denote a triangular and symmetric uniformly varying load of ordinate 0 kN per meter at the ends and ordinate W kN per meter at the center of the beam. Without going for the static equilibrium equations, it is easy to understand that the reactions at A and B are half the total loading value based on symmetry of loading over the beam, that is, each of value W times L over 4 kilonewtons. Let's now mark an arrow pointing towards the right at reference end A with label X indicating the distance of the imaginary cross section from it. The ordinate denoted by question mark symbol of the loading at some cross section can be found from the similar triangles theory as question mark over X equals W over half L. Hence question mark equals twice W times X over L kilonewton per meter. We can now find the equivalent point load value of the shaded part as half times X times question mark, which can be simplified to W times X squared over L kilonewtons and acts at a distance of X over 3 from the section. We mark the zero datum lines for the shear force and bending moment and label them accordingly. The center point of the beam is marked as C. Now for region EC valid for X greater than or equal to 0 and less than or equal to half L, the shear force at X equals plus W times L over 4 minus W times X squared over L kilonewtons and is parabolic with respect to variable X. The double derivative is found to be negative in sign, hence the locus of the curve obtained is of a maxima type. We apply the limits of X for this region and find that the shear force at A is W times L over 4 kilonewtons, while it is 0 for the center of the beam. We hence join these 2 points by a parabolic curve of maxima type. The bending moment at X can be found for this region as plus W times L over 4 times X minus W times X squared over L times X over 3, which is equal to plus W times L over 4 times X minus W times X cube over 3L kilonewton meter and is cubic in nature. The double derivative of the bending moment equation is found to be negative, hence the locus of the curve obtained for bending moment also is of a maxima type. The value of the bending moment at the end A is found to be 0 and at the midspan of the beam, that is at point C, it is calculated as W times L squared over 12 kilonewton meter. We hence plot these values in the bending moment diagram and join them by a cubic curve. Now the shear force for the left part and the right part of the beam created by the section is found to be positive and negative in sign respectively due to the respective reaction forces acting at the supports but of the same value. Hence the parabolic curve is drawn between value 0 at the center and minus W times L over 4 kilonewtons at the end B for the shear force diagram but of a minima type of curve. Likewise, due to the reaction forces respectively for the two parts created by the section, we have a sagging moment induced. Hence the moment values shall both be positive in sign and we plot a cubic curve in the bending moment diagram for the region CB. It is important here to note that the shear force at X and the bending moment at X equations for region CB still can be written in terms of the variable X from the reference end A, but it shall involve 4 number of terms, both for the shear force and the bending moment as well, for which the calculations become very laborious. We hence skip this task and use the symmetry of the loading on the beam to our advantage to find the values for the other part as explained earlier. The lengthy equations for region CB, however, may be useful for programming, where computers utilize them for plotting the curves. The explanation of the theory for simply supported beams is hereby concluded. In the next lecture, we shall consider solving a problem of a simply supported beam with a number of loading types.